All right, everyone, we are back, and now it is time to actually look at some stress strain curves. So we've looked at kind of the atomistic basis and structure of materials, and now we're going to kind of be making the connection in terms of how does that relate to mechanical properties. So the atomistic basis of elasticity, lots of kind of fun topics, but all of these mechanical responses depend on internal forces and moments, external forces and moments. Those material properties are going to be dependent on the applied forces, but also on the atomistic basis and structure. And also our component geometry will factor in, but we're going to try to non-dimensionalize that when we plot stress versus strain. So when we think about the atomistic length scale that we discussed, that will affect essentially our stiffness is going to be related to this binding energy. Our yield strength is going to be dependent on presence of defense, as we discussed. But before we get into that, we want to kind of establish some common notation. So whenever you're working on mechanics problems, set up your coordinate system. So what is our 3D coordinate system? Is it 2D, 1D? We'll have to figure that out. Moments, first rank tensor property, because there's one hat here. Our moments, the key thing that we're going to be talking about when we look at moments, again, vector across with a force. Again, force is a vector property. First rank tensor property has direction and magnitude. When we think about moments, we're going to use in this class that the counterclockwise rotation is going to be positive. Our clockwise rotation is going to be negative. When we look at stresses, compressive stresses, and thus stress will be negative, strain will be negative. We'll talk about stress and strain in a bit. If we're in tension, if our material is expanding, the stress will be positive, the strain will be positive. And those are going to be our critical notations. Those are going to be our conventions. Now, in addition to this, we are also going to assume in this course that we are in static equilibrium. What does that mean? It means really that the sum of all the forces and moments must be equal to 0, and thus we're eliminating both translation and rotation. So we are in static equilibrium. Our material is not moving. Our material is not translating. Our material is not rotating. Now, it is changing dimensions, but it's not translating or rotating. So static equilibrium, these are our conventions. Set up your coordinate system, and we'll work through there. So next time we'll get into defining normal stresses and shear stresses, and then we'll see you in the next video. Thanks. Bye.